I didn't hit record.
Okay, well, we'll start over.
Bam, go.
All right. Hello, everybody. For this trig session today, we're going to focus on a few things. And the first thing we're going to focus on is some applications of vectors. And this particular problem here, work is force times distance. We can think about force vector times the distance vector. And because the force vector, so I can say, like right now, I can say W is the force times the distance. So force vector times the distance vector. But the force vector is not in the line of motion. You see, the motion is horizontal, and the force vector is made at a 30-degree angle. So let's see, it says 50 pounds, so that the magnitude of this force vector is 50 pounds. Okay, and the distance vector is the magnitude of it is 30 feet. Okay, so 30 feet is the the magnitude of the distance vector. So that force vector, what I'm going to do is I'm going to say 50, the magnitude times cosine theta. Theta being the angle between the two vectors, or you can think about it projecting along that line, that horizontal line. So cosine of 30 degrees. And I could just slide this over and put the 50 times the d is 30, then times the cosine of 30 degrees. And there's Dave doing it right there.
I just thought we'd want to see the formulae.
Exactly. That's a good idea. So if the force was in the line of motion along the horizontal there, you see that the angle would be 0 degrees, and cosine of 0 degrees is 1. So we could leave it off. But anytime the force is not along the line of path like that, the horizontal, then we have to say magnitude of F times cosine theta. We could say plus magnitude of F times sine theta, but sine theta, no, we wouldn't do that. Sorry. I was thinking if it was going straight up. Never mind. Forget what I'm saying. Forget what I'm saying. W is 1500 cosine 30 degrees. And let me write out what cosine 30 degrees is. Cosine 30 degrees is what? Square root of 3 over 2. 2 goes in this, what, 750?
750.
So I get, my work is 750 square root of 3. And this is what? Foot pounds.
Foot pounds.
And I guess we could approximate. You want to approximate this to, this is the exact answer.
1299.
We did it?
1299. Yep. And it's 0.03. So, I mean, you can just leave it as.
Well, I'll just do one.
Yeah.
Okay. All right. So there we go. Any questions, guys? It's pretty simple. Not very difficult.
I had a question. So, Professor Simon, you had a question on your book problems about rearranging to make the work more effective. Is that something like you could apply to this? And if you did, like, what would that look like?
So, like, the idea of rearranging, like, so the person is sliding this crate across the floor, and it looks like that vector is a pull. You see, because so it seems to me like maybe this person is standing in front of the crate and having a rope over their shoulder, but they're standing up above the crate. So when I say a rearrangement, like if you think about it, your brain actually already kind of wants to do this. If you're having trouble pulling something, what do? You get lower into the same line and you direct. So that's exactly what we would be saying here. Like if you could actually rotate this thing down further and make the full 50 pounds in the dimension of the distance. That's what Miss Flanders was saying a minute ago. Then you wouldn't have to worry about the angle, and you would just plain out multiply the two things together.
Yeah.
It would just be then 50 times 30.
1500. Yeah.
And you get the full 50 foot pounds, you see.
Gotcha. So that's like the football
kind of
players and getting down and everything, basically.
Right. And you're maximizing your work.
Right.
See, that would be the maximum value of the work.
Right.
So anytime, the closer you can get to the line of motion, that the better.
Okay, got it. Thank you.
Alrighty. Dave, which one you want to do next?
Let's do the well, the next one that's just like it. We can do the second close your door one.
Okay, second close your door.
By the way, guys, we're taking this from a textbook that's through the Wiley Company, written by Cynthia Young, to give them props here. This is by no means our problems. It is totally problems that have been created for us.
Yeah,
they have
borrowing.
been generous to allow us to use this book for our courses. Okay, so a sliding door is closed by pulling a cord with a constant force of 45 pounds at a constant angle of 55 degrees. So the door is moved 6 feet to close it. So this is very similar.
It's very similar. It's almost identical. Just the angle and the distance is different, but it's the same formula.
I'm just trying to picture what's going on here. So like you got this sliding door situation here, right? It's sliding this way, and there's got to be like maybe some sort of railing system up here that the door is attached to, and it's attached in such a way that something's being pulled here, but that means that the force is being acted at this angle, right, which is the 55 degrees here. So if you look at the way this is being arranged right here, the cord is attached at a point, right, and is pulling with 45 pounds, and then the door is sliding this way, and it's 55 degrees between them, right? 6 feet. So it really is identical to the last one. The work is going to end up being the dot product, but to do the dot product, we have to multiply the magnitudes and then the cosine of the angle between them. This one just isn't a memorized angle is all. So 45 times 6 times cosine 55 degrees, 154.86. So let's just do the nearest whole number. 155 foot-pounds.
Okay, I'm going to snip that.
Hang on.
Oops, sorry.
It was just a little messy, and I'm being picky.
Okay. Okay, you can erase, Dave.
Do you want to do the breaking one?
Whatever you want.
Nice.
Okay, which one?
The breaking one? You want to do the breaking one?
Sure.
A car that weighs 2,500 pounds?
These are all pretty much the same.
This one's different.
Oh, let me see what this one is.
This is the one that originally caught my eye. Why I suggested we use some of these problems out of the book we'll be adopting next semester.
Let's see if I can do it. Might need some help. Seriously, because it said it's different. Let me see. I don't know. I haven't read it yet. So number 3 here. Okay, I'll put my glasses on. car that weighs 25 pounds is parked on a hill in San Francisco with a slant of 40 degrees from the horizontal. How much force will keep it from rolling down the hill? Well, it's not a work problem.
Nope.
It's just really a projection kind of problem. So let's go ahead and draw it. A car that weighs is parked on a slant. So we have this slant. This is 40 degrees here. And we have this car that's 2,500, pounds here. So how much force will keep it from rolling down the hill? So it's basically, it's kind of part, these work problems are a little bit harder. It's basically whenever we said F dot D, that F part is the 50 cosine 30 degrees. And so that's basically what this is. We're going to project this 2,500 along the right. So Dave, right, it's like this. Well, I meant to say, sorry.
The 2,500 is not along the ramp.
It's not along the right. So it's 25. Let me think about my notation. It's 2,500 cosine 40 degrees.
You're not going to want to do it that way.
Huh?
You from your hill, say the truck is here, the 2,500 is here.
Yes.
And it's at a right angle. And you want
to I have to use this angle. Sorry.
And you want to project it onto the ramp.
I want to yes. Wait.
No.
I've done these problems before. Hold on. Guys, don't write anything down. Is that right? That long discussion.
Right, there we go. Now
okay, here we go. So one way you could look at this is looking at the force, that 2,500 pounds, the weight of the car. That weight is due to gravity. Gravity points downward, so that 2,500 is pointing downward. So we want to know what force will keep the car, here's the car, from rolling down, rolling down the hill. Okay, so if we project that force vector along the line of the ramp, we'll get 2,500 cosine of 50 degrees, because that, you can think about this vector right here, and the angle would be 50 degrees. So 2,500 cosine 50. Dave, you can go ahead and add something to that.
No, that's the that's
I don't know what I didn't do it in my calculator.
The 2,500 cosine 50 is correct.
So what do we get? So you want to work it how you would work it with the 40 degrees, but if you use sine theta.
Let me do the next problem, and I can do I'll do it that way. So
go to my calculators in.
This way you did it your way. You problem solved it, like put it together.
I think that I always use cosine. That's why
Yeah, that's fine.
So you guys, you get 1606. I'll put 0.97. I'll do 2 decimal places.
Ooh.
And this is just pounds. This is just a force. So it's not foot pounds. We're not doing work. We don't have a distance involved right there. We're just looking at a force.
Mm-hmm.
So obviously, I'm thinking that you guys should know you don't have a force. The force is less than the weight of the car. So I mean, I can kind of figure out, it's close to whatever 1,600, but it's not the total weight of the car. So it should be less. And you can kind of think about that, because I always think about my answer. Is it reasonable or not? So if I got to answer 3,000, I'm thinking, okay, that's not reasonable. So if you have a 2,500, that would be, enough, you'll be safe, but this is the minimum force needed to hold it up. All right, I'm done. Which one you want to do, Dave?
Put down the towing power one.
Towing power.
Oh
yeah, which one? The first?
2,500. It's
first or second.
Problem down.
Which one?
It's the next one right underneath the braking power, the 2,500 pound one.
Okay, a car. Okay.
It's the same thing except this one.
Oh, it's same thing. We're gonna okay. Then we're gonna multiply it times 120.
But I'll do it.
I'm sorry if I gave it away.
No. You can.
Just,
But I'm gonna do it my way.
okay, go ahead. That'd be great.
All right.
Let's put a little.
So
Number 4.
we need our pictorial again, right? Like this, 40-degree angle. The truck is somewhere, or is it a car? Whatever. Car's here, right?
Yeah. Car's so much better than mine.
I don't know. Zoom in. It'll look pretty bad.
Mine was a block on wheels.
Hang on. Let's give it a little fin in the back. You know, it'll be really...
Okay. Be all fancy. Go ahead. Outdo me. It's okay. I am no artist.
Okay, so it has a weight vector here, and the weight is 2,500 pounds. So the weight vector is 0, negative 2,500, right? If you think about down as negative, the negative here is just a directional indicator in this case. And in the end of the day, we're going to end up dropping that negative because we're only doing magnitudes here anyway. So next we have that we want the truck wants to move the car. So we need a force and a distance. I do have some reservations about this, although the fact that a vehicle doesn't totally have to worry about friction is kind of the way they're getting away with it. You need more than the force that it takes to keep it steady, though. So here's the thing. The amount of force that it takes to move the thing technically should be a little more than what I'm about to compute, but I'll show you what I mean in just a second. So right now, I'm going to compute again what we just talked about, which is the amount of force that it's going to take for this thing to stay stationary, right? So I'm going to have a ramp vector here. My R ramp vector is going to be cosine 40 degrees, comma, sine 40 degrees. And that just represents the direction of the ramp. For me to get the force that I'm interested in here, the piece of the force that is projected from the weight here, okay, I'm going to get the magnitude of the projection vector. So the magnitude of the projection of W onto R here is just going to be W dot R divided by magnitude of R. However, the magnitude of R here is 1. R is a unit vector because it's just a cosine and a sine. Cosine squared plus sine squared is 1. Since it's a unit vector, the denominator here is just going to be 1. And W dot R is going to be 0 times the cosine, so just 0. And then minus the 2,500 times the sine of 40 degrees. So you should recognize the number that comes out of this. And actually, I'm going to be doing the absolute value of this, not just, and that's because the negative doesn't matter. I'm only doing a size of a projection here, right? So I'm gonna put the little p here. That's the projection vector right there. Okay, so the size here, 2,500 times the sine of 40, gives us that 1606 again. I'm just going to say, well, I'm going to carry it out because it's not the final answer. 969024. Okay. Now that's the amount of force that it's going to take, get this, to hold it there. Technically, to move it, we would need to have the slightest bit more okay? And notice they don't say how fast they're moving the car, because by the way, that matters, right? If I'm going to move the car faster, it requires more work. They really needed to word this problem better, but I think they were also afraid of getting too physicsy, if you know what I mean. So here's what I'm going to do. I'm going to round up to my force here, magnitude being 1607. So technically that's larger than the thing we just calculated by a very smidgen little bit. But since the car is rolling, you don't have to worry as much about friction. It's just going to start moving. Okay, so I'm going to use the 1607, but by the way, that car is going to creep up that hill with just this small amount of force that it is slightly larger. Okay, so if you want to move it faster, we'd have to do way more pounds than this. Okay, but then the work that they're talking about is going to be that magnitude of the force times the magnitude of the distance times the cosine of the angle in between them. But take a real close look. They said that we're just moving it up the ramp. So the distance vector and the force vector, Abby, like we were talking earlier, they're in line together, right? So I don't even need to worry about the cosine of the angle. That's going to be times 1. So all I'm doing here is I'm going to do 1607 times the 120 feet, right? And I'm going to get 192,840 foot-pounds. Okay. Now, again, slowly moving. You would need more foot-pounds to make it move faster. We're just barely breaking the weight counterbalance. Okay, so I just recalculated the last problem a different way, just to show you that there was another way, and then force times distance gave me the work. Just in time, Vicki.
Okay, I'm so sorry. I really am. That was my elderly daddy, and I need to answer his phone call.
It's fine.
Whenever it comes in, I need to answer it because I don't know.
We just finished, so go ahead.
Yeah. Okay. He took a fall.
Ouch.
Yeah.
Okay.
And he had to go to the emergency room, but he's okay. He's just badly bruised. Anyway, I don't know if I should be saying all that on the video.
Oh, probably not.
Sorry, I'm just getting. Okay,
Yeah.
you can erase it.
I understand you're getting flustered.
Yeah, so much going on. Okay. All right, and I missed, some of your thing here. All right.
You can watch my other lecture videos if you want to.
No, I got it. I know exactly what you're doing. You're just actually doing the well, no, I thought you could actually do the dot product, but you still did the
I did.
projection.
See W
Yeah,
dot
I
R?
see it. Yeah, I see you did that. Okay. Looks
That's
good.
just to find the force size. Yeah. Okay.
Yeah.
You want to go ahead and move on to the
Yeah, I think we should because it's already 3:40. And this is good problems. We got some good problems there.
Go ahead and
All right.
do a converting of a point and stuff, and then I'll do a couple of converting equations if you want, or one.
Okay. Do you have some problems picked out or what?
No, you can
Just make them up.
Yeah. Or yeah, just
Well,
make.
I can just make these are easy just to make up. So well, I can actually do a text box here. Right, if I just start typing, I think I can well, then I have to use the right notation. I'm not going to do that. Sorry. This is draw. So if I have vector v from the point, let's say -2, 3, 2.
Oh, okay. I thought we were doing polar stuff.
Oh, that's in vector.
We did the vector stuff.
Oh, you're just doing vector applications. So I'm sorry, Dave. What'd you say? Polar, like a point?
Yeah, like
Convert a point. Okay, so given
4 and 11 pi over 6.
Yeah, let's do this. 4, 11 pi over 6. Okay, so first thing I want to do is let's plot it. Okay, so you don't have to be too technical, you know, with this here. We just need to see. So here's my set of, you still could call these XY axes. And I have this 11 pi over 6, so that's, you know, let's call this, you know, 11 pi over 6. Okay. The reason I drew across in quad 2 is because a lot of times if in fact if I had a negative r, so I'm going to use this over here. This is 5 pi over 6. All right. Where's my radius? 4. So I just thinking about, think about 4 circles. So this would be 1, 2, 3, 4. So that point would be right here. 4, 11 pi over 6.
Okay.
All right, do I have any questions? Okay. Now let's do some other representations.
How about where the r is negative, but it's the same point as what you just drew?
All right, so let's find another representation where r is negative and you want theta to be between 0 and 2 pi. So we need a so let me do this. So here, you know, this was the rotation 11 pi over 6. So let's do a negative r with a positive rotation. See, the negative r makes it, oops, I wanted to get it red color. The negative r would make it land opposite the pole on the same line that the terminal side of theta, but on the opposite the pole, which is actually 5 pi over 6. So this point would be -4, 5 pi over 6. I should have done that in green. So this would be -4, 5 pi over 6. And then let's do another notation.
I can
Yes.
graph that one out real quick too.
What's that?
I can graph it out real quick.
Okay, let me do one more.
Go ahead.
Let's find a representation. Let's do both negative, where r is negative and theta is negative. So if theta is negative, I have to rotate clockwise, but r is negative, so I can't stop on, you know, I got to go all the way over here. So that would be what? That would be -4. Well, that would be negative what? 7 pi over 6. Right, guys? And I could do one more. Well, I could do infinitely many, but I'll stop there, Dave. If you want to.
Positive and theta is negative, yeah.
Yeah, we could have done that. But let's go ahead and graph it with GeoGebra. And guys, I want you to notice that the point never moved. Just with a negative r, I land on the line of theta across the pole, like 180 degrees
Right.
across the pole, directly across.
Here, I'll make that obvious with this too.
Okay, go ahead.
Let's see. Which one do I want to show? This one. Okay. So can y'all see that GeoGebra? Okay, so this is one of the GeoGebra things that I have already pre-made. Notice that what I can do is I can change the size of R. Okay. The first thing I want you to note about that is R always generates from the center. So R equaling 0 is the origin, no matter which way you're facing. And R positive just goes in the direction of the angle. See where the angle is here? So R positive goes in the direction of that. And R negative goes opposite. The angle is still over here, but R is now pointing in the other direction. So the first one that we did was R was 4, right? And theta was 11 pi over 6, was it, Vic?
Yes.
So that's 330 degrees.
Mm-hmm.
So that's right here. That's the original point, okay? Now, if you want to see how this is the same, I'm going to leave R as 4, okay? But I'm going to make it negative. Watch what happens. It bounces it just to the other side, right? But then if I change this angle, what was it? 5? No, it wasn't.
150.
It was 5 pi over 6, wasn't it?
Yeah.
So
Yeah. 5 pi over 6. So 150. Yeah.
Notice
See?
it's right
Because
back in that same position again. The only thing that's changed is the angle, the way it's displayed. And then another one was R was -4, and this angle right here was -210.
210.
Yeah, because it's 7 pi over 6, right?
Mm-hmm.
Nothing changed.
Yeah.
See?
Well, you're still highlighting 150. Does that matter?
Oh, hang on. Oh, you know why? Because it may have converted it. Yeah.
Yeah, I guess it did. It just makes, yeah. Okay.
It converted this angle right here into
It just knows to use that angle too, or whatever. Maybe just convert it to the
but
positive.
me changing it didn't affect.
Didn't change what, yeah.
Right.
That's cool.
Right.
Yeah.
See, it's still affected by it, but it only wants to give the positive answer is why.
Yeah.
It likes doing things like that. So anyway, that was the whole point that she was trying to get across to you. Also, Vic, what about converting it back into rectangular?
Yeah, let's go back to that. So let's convert it to rectangular. So I'll pull this up. And if I want to convert it, let's call this part D. Let's use a different color, maybe purple. Convert the point to rectangular. Okay. Well, X is R cosine theta. These are old, you should know these formulas from the very beginning of trigonometry, right? It looked as if X over R is cosine theta, Y over R is sine theta. So just a little rearranging in this equation. And I get X is 4 cosine of 11 pi over 6. Y is 4 times sine 11 pi over 6. So 11 pi over 6 is in what? Quad 4 with a reference angle of pi over 6. So that's going to be positive square root of 3 over 2. So X is 2 square root of 3. Y is 4. Now sine of 11 pi over 6 is going to be negative. So I get Y to be -2. And I saw this on there. So my XY is 2 square root of 3, comma -2.
Which would be?
And 2 square root of 3 is approximately what? I saw it.
3.46.
Let's see. 2 times square root of 3. You get 3.5. Yeah, so about 3.5.
Okay.
If you go back to your GeoGebra.
Yeah, I pulled it back up.
Okay. Go ahead and share your screen.
Just look at the coordinates right here.
Yep.
See, it's on that point, and I put it back to the original R equals 4, theta equals the 11 pi over 6.
Pi over 6.
Mm-hmm. So you can see the coordinates of the actual point there.
Yep, looks good. So that looks like we converted it correctly.
Mhm.
So good.
Yep.
All right, don't forget to put your names in the chat, Han and somebody else on iPhone and Lincoln.
One more.
Put your names in the chat so
Yes, I
we get
forgot.
that data that you guys are here.
Back up again, and let's do one more. Let's do a conversion of an equation, Dick.
Okay, which one? Oh, you want to do? Let me see. Let me pull up the share screen. No, that's not right. Share screen. Where's my OneNote? Here it is.
There it is.
There it is. Okay. You want to just go ahead and write?
Yeah. Okay. So whenever you're ready.
Yeah, I'm ready. Go ahead.
So what we have is the function y equals 3x squared, and we would like to write that in a polar format so that I can graph it in polar coordinates. And that graphs the thing completely differently than what you're accustomed to. It goes, in the natural. And once I've converted it, I can show you in my program too.
That's the same graph.
Right.
Yeah.
So remember, y is r sine theta, and x is r cosine theta in our system there. So if I use both of those, I'll have r sine theta is equal to 3r squared cosine squared theta. Because x is squared, I'm just going to square the r and the cosine by distributing the exponent. So what I do from there is I bring the r sine theta over with subtraction, like so. I factor out an r, like so. And then since this is equal to 0, I can split and solve. So either r equals 0 or 3r cosine squared theta minus sine theta equals 0. Of course, r can't equal 0. That would mean that we're just graphing a singular point there at the origin. So if I solve for r here, that would mean that I would add the sine theta to the other side. And then I would have to divide by 3 cosine squared theta to get r by itself. So then I would have this in polar form. So sometimes there's, a little trick or a maneuver, like you can use a Pythagorean identity in cases where it's circular and things like that. Sometimes you just have to straight plug and do whatever you can to solve for your r variable. Did you grab it, Vic?
About to.
So that I can bounce over and graph it and be done.
Yeah, but wait, I botched it.
Try again. By the way, why was the cat disqualified from the race?
The cat?
Why was he disqualified from the race?
I don't know.
He was a cheetah.
Oh. Okay, go ahead and erase that. Yeah.
Alrighty.
And this is a whole nother problem. What do you want to call this? What number is this?
I have no clue.
5, right?
So here is the polar graphing system here. And I'm going to change the r function that we're graphing here to the thing that we just solved, which I believe it was sine and divided by 3 cosine squared, right? I believe that was it. So then don't forget what's going to happen is I should still see a parabola here if I entered it incorrectly. That would be the only thing I'd be worried about here. We should still see the parabola y equals 3x squared, which is what you're customarily used to seeing the parabola through the origin. A little bit skinnier than usual because the 3 stretches it. Okay, but it's going to draw it in a rotating pattern. So you'll see the theta here is going to rotate. And as it does, the r is going to go out to drawing the parabola. And at some point, it's going to go off to infinity and then appear on the other side. So look, there it's going. See, the r starts off really small, and then it's going to take off here. There goes the top of the parabola. It goes off, it goes around and comes back down. And it gets back to that center point right as we get to pi here. Right there. And then it proceeds to draw the shape again. This is what I tend to call more of a projective approach to these things. Imagine a parabola just being a stretched ellipse over the back of, like, say, a planet as you look from the outside of the planet. It would be just like that. It would be like you'd see it and then see it come back down, but you don't ever get to see the other side of the ellipse, of the oval. You know, the parabola is sort of like that. But this is the like if I were to type in to just graph y equals 3x squared, right? Let's see. Let me get it to shut off here. See, there's that. It's the same graph. Y equals 3x squared. Okay. Well, guys, thanks for coming. This was a fun, short little divot on vector applications and polar coordinates.
Thank you.
Mhm.